Hello, class. This is Tim Tomlanovich again. So this is a lecture to talk about homework set 7. This is in learning plan 5. Okay. So we're going to start mixed design, concrete mixed design, PCC mixed proportioning. Well, it's not mixed design, it's proportioning. So, okay, the absolute volume method. Okay. So what I'm going to do is I'm going to talk through these steps and walk you through these tables. And what I'm going to do is I'm going to go through the examples, which I have attached in Blackboard. Okay. All right. So PCC mixed proportioning. Okay. Number 1, specified compressive strength, F prime C. Okay. So basically what that is that I specify a design strength, and that is the 28-day unconfined compressive strength of the concrete. So it's typically 4,000 pounds per square inch, anywhere from 3,000 pounds per square inch to 4,500 pounds per square inch in our typical Green Bay area. Okay. Now, if you go to talk about high rises downtown Chicago, okay, we're in upwards of 10,000 pounds per square inch. Okay, so if it is not specified, select F prime C from table 15.1. Use the maximum value if more than one applies. Okay, so if I don't specify a mixed design, we got to decide where is that concrete being placed. Okay, and we got to pick the largest value. All right, so if I look at the exposure category, F0, S0, W0, C0, concrete protected from exposure to freezing and thawing, application of de-icing chemicals or aggressive substances. Okay? All right, so obviously this does not apply to Wisconsin, right? Because we have freezing and thawing. So I'm thinking Florida, Arizona, okay? Florida, aggressive substances. Is saltwater aggressive? Yes. Okay, so that doesn't apply. So we don't want to be by saltwater. So I'm thinking Arizona in a warm climate. This is where this exposure condition will um, apply to. Okay, de-icing chemicals. So that's obviously in northern climates. Okay, so if it's free of it, so we could categorize this exposure. So if you read here, maximum water cementitious material ratio, water cement ratio. Okay, select water cement ratio on the basis of strength, workability, and finishing needs. Okay, minimum design compressive strength. Select strength based on structural requirements. So that's what I was talking about before, structural requirements. So if there's no aggressive substances, there's no de-icing chemicals, and we're not in freeze thaw, basically I'm gonna pick the design strength, okay, that I select for structural design. Okay. So cementitious means because it could be fly ash, it could be cement, it could be gypsum. So that's why they use that term there. Okay. All right. So let's look at exposure category W1 and S1. Concrete intended to have low permeability when exposed to water, W1, or moderate sulfates, S1. Okay. Concrete intended to have low permeability. Where would that be? If you all our foundations are below the ground, okay, in the spring, right? We have groundwater tables, so we do not want water leaking through our concrete, getting into our basements, okay? Possibly a small dam structure, okay? All right, so that's what that would categorize that. So we don't want water flowing through that. Moderate sulfates, okay? Because sulfates, remember, it's the sulfate chemical SO4, right, will actually deteriorate concrete. So in our clay soils here in Green Bay, we actually have moderate sulfates. So because of the Leo Frigo Bridge failure, that was part of that, we would test our soil to make sure that we would have moderate sulfates. So typically, this will tell us what kind of cement we're going to use too, which is type 2, which is moderate sulfate. Okay. So if we're in that situation where we have moderate sulfates, yes, which we do in Green Bay, and need low permeability, a basement wall, yes. Okay. We want our maximum water cement ratio to be 0.50 and our minimum design strength of 4,000 pounds per square inch. Okay. See, PSI is in the parentheses, okay? So if I say I need a design strength of 4,500 pounds per square inch, but my exposure level only requires 4,000 pounds per square inch, I would choose the 4,500, right? You got to pick the maximum value, maximum design strength. Vice versa. So say I only need 3,000 pounds per square inch concrete for my foundation wall, but I know I need low permeability. It's telling me I better design it for 4,000 pounds per square inch. So I would use that value for specified compressive strength. Okay. All right, F1 exposure, concrete exposed to freezing and thawing with limited exposure to moisture. All right, so if you're up on a hill and you're not dealing with groundwater, that's the case, right? Limited exposure. Okay, sometimes you have it, sometimes you don't. Limited. That's a great term, right? So our maximum water cement ratio is 0.55, and our design strength our design strength is 3,500. Okay. F2, S2, concrete exposed to freezing and thawing with exposure to moisture, F2, or severe sulfates, F3. So one or the other, or both, okay? So in Green Bay, concrete exposed to freezing and thawing with exposure to moisture. That's typically us, right? It rains, right? We get groundwater. Our foundations are typically exposed to moisture. So typically we are in the F2, all right? Severe sulfates, we're not quite there. Okay, some spots, but we're typically in F2. So we need a minimum water cement ratio of 0.45, or a maximum, I'm sorry, maximum, and a minimum design strength of 4,500 pounds per square inch. So I'm going to choose this guy. Okay. All right. F3, S3, concrete exposed to freezing and thawing cycles with frequent exposure to water and exposure to de-icing chemicals. Would you say our roadways? Yes. Or very severe sulfates. Our roadways, right? Our roadways. Okay. Yes. Even in some spots it's frequent exposure. So if you look here, look, we go from F2 to F3. We go from with exposure to F3, which is frequent exposure. Okay, if you look here, the water cement ratio goes down and the design strength goes up. Okay, so that's a decision you need to make. How much exposure of moisture do we have? Okay, so is it better to be conservative? Yes. So for me in Green Bay, Wisconsin, if your sump pump is running all the time when it rains, I would put you in here. If your sump pump barely runs, I'd say you could probably do it here. Okay, do the F2 category. Okay, or if you're we got severe sulfates or very severe sulfates, S2, S3. Okay, so I think this is supposed to be S2 here. All right. C2, for corrosion protection for reinforced concrete exposed to chlorides. Yes, seawater, de-icing salts, our roadway, salt water, brackish water, seawater, or spray from these sources. Okay. So our water cement ratio of 0.4 and our design strength of 5,000. Okay. So that is step one. What is my design strength? Specified compressive strength, F prime C. Okay, so the structural design will have a specified strength to hold the loads, and then we'll have a minimum design strength based on the exposure category. You pick the highest of the two. Okay, so that's step one. All right. 2, required average compressive strength, F prime CR. Knowing F prime C, okay, that's from step 1. Okay. Determine FCR from table 15.10. All right, so less than 3,000, 3,000 to 5,000, over 5,000. So basically, we're going to take that F prime C value and add 1,200 PSI. What this is a factor of safety. Okay, so we make sure we get at least that value. This is a factor of safety. Okay, so you want to add, so for example, if I'm in an exposure category F3, They're recommending a design strength of 5,000 pounds per square inch. Okay. What I'm actually going to design that concrete for, throw 3,000 to 5,000 is 5,000 plus 1,200. I'm going to design it for 6,200 pounds per square inch. Okay. To verify that I get a minimum of 5,000. Okay. So that's part 2. Okay. This is that factor of safety. All right. That's how this table works. All right. Step 3, water cement ratio. Using F prime CR to select a water cement ratio from table 15.3. All right, where's 15.3? All right, compressive strength at 28 days. All right, so here's your compressive strength. And then I got to decide, am I non-air entrained concrete or am I air entrained concrete? If you're in any kind of freeze-thaw environment, you're going to be in air entrained concrete. If you're in a warm Bahamas area, you're not going to have air entrained concrete. Okay, so pay attention to that. All right, so what happens? Okay, if I look here, 6,000 to 72, so I'm at 6,200 pounds. I got a linear interpolate between these two numbers. Okay, all right, for non-air entrained concrete. However, if I look over here, the lowest water cement ratio for air entrained concrete is 0.32. There's nothing smaller. So if I'm 6,000 pounds per square inch F prime CR or greater, my lowest water cement ratio is 0.32. Okay? So first of all, you look at what the water cement ratio is based on your F prime CR. Okay? All right. Also check maximum values of water cement ratio from tables 15.1 and 15.2. All right. So depending on my category, right, this also gives me a water cement ratio recommendation. So I have my water cement ratio calculated from table 15.3. Okay. I have my water cement ratio from table 15.1 based on my exposure category. And then I have basically, if I have sulfate exposure, this also gives me a maximum water cement ratio. So looking at those 3 water cement ratios, I want to pick the smallest water cement ratio, the lowest water cement ratio, because that'll be the best concrete. Between the sulfate exposures to exposure category to design strength, I picked the lowest of the 3. That'll make my concrete be able to resist exposure, resist sulfates, and maintain its design strength. Okay, so that's step 3. Okay. So an example, we will go through this, okay? Maximum coarse aggregate size. All right. Check the size of coarse aggregate available for use. The maximum size of any coarse aggregate should not exceed, okay, 1/5 of the narrowest dimension between the sides of the forms. All right, so basically what I'm doing is I'm measuring from here to here, okay? So my coarse aggregate basically is, so I'm measuring the narrowest dimension between the sides of the forms, side of form to side of form. So if that's 8 inches, I take 8 times 1/5 of that. That is the maximum size coarse aggregate I can have for that aggregate to make sure it actually has room to fall in my wall. Okay, otherwise we're going to get honeycombing. 3/4 of the clear space between individual reinforcing bars and fabric, right? Reinforcing bar right here. So 3/4 of this spacing, 3/4 of this spacing, 3/4 of this spacing. So you pick your smallest spacing, right? Times 3/4, that is the maximum size of my coarse aggregate. Because why? Otherwise, it's like a sieve. It'll get hung up on there and it will not create a concrete wall. It'll just be all the aggregate will be sitting on the reinforcement. It'll be just sitting here, right? That coarse aggregate has to fall to the bottom of the form. Okay? 3/4 of the space between reinforcement and forms. 3/4 of the clear space. Okay? So wall form, edge of reinforcement. Okay? So 3/4 of that. Okay? So typically, otherwise that'll get hung up there. That coarse aggregate will get hung up between the wall form and the reinforcement. Okay? And then if we don't have any forms, 1/3 of the thickness of the slabs. All right? 1/3 of the thickness of a slab. Okay? So if I look at these pictures, right? So 3/4 of the distance between the reinforcement, 1/3 of the thickness of the slab. Okay, the distance clear. So we need to have clear space between the wall form and the reinforcement. Clear space between the reinforcement, and make sure we have our course aggregate isn't too thick based on the thickness of the slab. Okay, so kind of different examples. Can you imagine what's going on if this aggregate's too big? It's all going to sit on top of that reinforcement. So we want concrete around it. Okay. All right. So hopefully these pictures help clarify what I'm talking about. All right. So that's a check. All right. So if I give you two sizes of coarse aggregate, we got to whichever one works. Or can we use both, or can we use one, or do we got to find another source? Okay. So that's depending on what the supplier has. Okay. All right. Step 5. Maximum air content. Use the maximum coarse aggregate size to be used to select the target air content for air-entrained concrete from table 15.5, 15-5. Add 1% air to the target air content to allow for -1% to +1% air for air-entrained concrete. For non-air-entrained concrete, so if we're in warm weather, right, we're not going to air-entrain it. We're going to air-entrain it if we're in cold weather, right? Freeze thaw. Select the amount of entrapped air from table 15.5. Do not add 1% air to the values. Don't forget about this. If I'm not non-air entrained, do not add 1%. All right. So maximum coarse aggregate size. So let's look at this table. Okay. So 15.5. So this is my slump, 1 to 2, 3 to 4, 6 to 7. Okay. All right. Water. So here we go. We have water pounds per cubic yard of concrete for indicated size of aggregate. Okay. So here's our aggregate size: 3/8, ½ inch, 3/4, 1 inch, inch and a half, 2, 3, 6. Okay. Here is our air, and so this is the water value. This is our air and train value. So if it's non-air and train, I look at my coarse aggregate size, the maximum coarse aggregate size I'm using, and this is my air, and this will be my entrapped air. I do not add 1%. If I'm using air and train concrete, I find my maximum coarse aggregate size. Okay. I find my exposure, right? Mild, moderate, or severe. Okay, depending on the aggregate size. So say it's 2 inch, I'm going to use 5.0% air content. I'm going to add 1%. Okay, so I'm going to design for 6% air content. So that's how that table works. Okay, so that's step 5. Step 6, if none is specified, select an approximate slump from the following table. Okay, so here we have a list of tables here. Mass concrete, it's like a big dam. Maximum slump, minimum slump. Okay, so contractors love to work with concrete that's has great consistency and workable. Okay, so we do not want a stiff slump because one, it's a great likelihood that we are going to have honeycombing and consolidation issues. So we want the highest slump possible. Okay, so if we know ahead, if we want a high slump possible, we can design have that much water in there because our slump determines our water cement ratio. We want a low water cement ratio. Okay. But if we don't want a high slump, but we need to get that concrete workable, we're going to add an admixture. Okay. So if I don't specify a slump, we're going to pick it off of this table. Okay. Step 7, water content. Use the maximum coarse aggregate size to be used to select the water content in pounds per cubic yard, PCY, for either non-air entrain or air entrain from table 15.5. See step 5 above. This value for coarse aggregate that is completely, this value is for coarse aggregate that's completely angular, crushed. Reduce the amount listed in table 15-5 by 20 pounds for subangular aggregate, gravel with some crushed particles, or 45 pounds for rounded gravel. So basically, okay, so let's go back up to 15.5. All right, I have 1 inch, I have a 1 inch maximum aggregate. I'm in air and train concrete, and I want a 3 to 4 inch slump. Okay, so if my coarse aggregate is completely crushed, I'm going to add 295 pounds per cubic yard of concrete. Okay, however, if my aggregate is subangular, I'm going to take 295 pounds. Remember, that came from this table right here. Right, where was I? Right here. Okay. And I am going to subtract the respective value if I have some crushed particles, subangular aggregate, or rounded gravel. Okay, I'm going to subtract that amount of water. Some pounds, that's pounds. Okay. All right. So rounded gravel has less surface area, so there's less cement to coat. So that means we need less water to hydrate the cement. Okay. So that's step 7. All right, step 8, cement content. Knowing the water cement ratio. Remember, that was all the way from step 3. That is our lowest water cement ratio. Water cement ratio. The following minimum, calculate the cement content in pounds per cubic yard. Okay, that's a ratio. So if I know how much water I'm using per cubic yard and I know my water cement ratio, I can do algebra and calculate how much cement I need per cubic yard. All right, so these are in the, so where all this information is coming from is actually coming from your book, your textbook, okay? What I did is I actually combined it all into this nice sheet for you, okay? And there's additional information in there, all right? So you want to make sure that I have a minimum of 564 pounds per cubic yard of cement for a severe freeze-thaw, de-icer, or sulfate exposure. So if I don't have that, based on my other design criteria, I'm going to bump it up to that, okay? If I'm going to place concrete underwater, I want to make sure I have at least 650 pounds per cubic yard. And then for flat work slabs, okay, use table 15-6, which is right here, okay? So maximum, and this is based on maximum coarse aggregate size, all right? So that's how I know how much cement I'm going to add per cubic yard. Okay. All right, hopefully this will make sense when we do doing an example. So just going to take a little short break here.